All right, so let me thank the organizers for inviting me here. It's actually my very first time in India, so I'm very excited to be here. I am very jet lagged, so if I say something outrageous, you can blame the jet lag. All right, so today for those lectures, I want to talk about this topic of entanglement phase transitions. I will define precisely what I mean by this. Okay. So I mean, I should say like the whole theme of the workshop fits my research pretty well. But today I'm not going to talk about hydrodynamics. So I'll talk about this on Friday. And so mostly I'm going to talk about things that are related to thermalization and many-body localization. So this will also naturally continue Maxim's lectures yesterday. All right, so, but I'll try to, I won't talk only about MBL, and I'll try to phrase this more generally in terms of what I call entanglement transitions. Okay, so I'll try to kind of introduce the idea of phase transition and criticality into the mix in terms of what you heard about in terms of thermalization, localization, and so on. So, okay, before I kind of go further, let me just briefly kind of introduce what I mean by this, okay, just to give you a vague idea, and then I'll go into the details. So when I'm going to talk entanglement transition will be a new type of phase transition where entanglement is going to play a crucial role, as you could expect. And so more precisely, I'm going to define this as a type of phase transition where there's a dramatic change in entanglement patterns between the two phases. Okay. I will define. So of course, with a definition like this, you could include, say, phases from transition from trivial to topological phases, where you have a different type of entanglement structure when you have topological order. But I'm going to actually talk about something way more dramatic than this. And so in particular, I'm going to talk about transition where you would go from scaling from volume law to area law entanglement. Okay. So this is not the only type of phase entanglement transition you could talk about, but that's what I will focus on today. So I'm going to think of like a system where you can tune a parameter, and either in the dynamics or in eigenstates, your entanglement structure will change from having area law to volume law. And so I'll give a few physical examples of this. So one example related to what Maxim talked about yesterday is the many-body localization transition, but I will give more examples. Okay, so you can think of those as being entanglement phases. And so you can think that entanglement will be kind of our order parameter, even though there'll be no order parameter in everything I talk about. Okay, but really everything that's going to change will be about entanglement. We'll have nothing else. So I should say I'm also going to focus on 1+1D systems. This is not needed, but will make my life easier. Okay. So all the examples I'm going to talk about will be in 1+1D. So, okay, so the first thing you can ask about is, okay, if those things exist, why would they be interesting or why would they be different from what you know, okay, from ordinary phase transition? So the first thing you can easily think about is that those phase transitions will have to be dynamical in some way. Okay, and so the reason is that gapped ground states of Hamiltonians always have area law. And so normal phase transition are always from area law to area law in some way. So if this occurs, it has to be something that has to be either about dynamics or excited eigenstates. So those transitions I'm going to talk about will have nothing to do with ground state physics. And they will be dynamical, and they will be neither quantum nor classical, really. Okay, so they kind of don't really follow the usual nomenclature of phase transitions. And if anything, you can think of them actually as being kind of transition between quantum or classical. What I'm going to talk about are real transitions, okay? And there will be critical exponents and universality. So yeah, but I'll get to the examples before I. So I'm gonna, okay, so the 1 plus 1D will be just, okay, you'll see, just because I want tractable examples, but some examples I'm gonna talk about easily generalized to higher dimensions, so just to make things a bit more tractable. There's no, okay. So those transitions, like I said, are kind of classical to quantum in some way, and you can kind of decide whether you want to call this quantum or this one quantum, depending on your taste. If you want to talk like highly entangled, volume low, something more quantum, and this one more classical, or the other way around. In the context of MBL, sometimes you call this more quantum because it has coherence, and this one would be ETH and more classical-like. Okay, so all right, so my main motivation for trying to think about transitions like this is that they are entirely new, in the sense that it's not like merely a new universality class or something. It's really a new type of phase transition in this way. And if you have phase transition and you're a good physicist, of course, the first questions you want to ask is whether you have universality, classification, whether we can compute critical exponents, is there some renormalization group structure underlying all of this, can you write down a field theory, and so on. Okay, so those are the questions I'll try to address, and we don't have full answers, full examples I'm going to talk about, but I'll try to tell you where we are. Okay, so our question will be universality. Okay, so this will be universality at high energy density, very far away from the ground states in dynamics. Can we classify them in some way? Okay, so is there anything like something like a Landau theory? Do symmetries matter? Maybe in some cases, I'll show you we can actually write down some field theories, or just kind of more broadly, can we think of a normalization group? We have physics, and of course, what are the physical realizations of this? Okay. So those are the main questions I will try to address. Okay. So in some cases, I will show we can pretty much do all of this, but in others, I won't get that far. Okay. All right, and I should say, like, all of those questions are highly non-trivial, again, because I'm talking about things that are very far away from the ground state. So there's no natural low energy or anything that you would usually have to write down the field theory or have a renormalization group structure. All right, so before I go further, I should give you some examples. And so those are the examples I'll talk about for the rest of the lectures, okay? And I'll get into more details. So just to be clear, I'm thinking that I'm going to be mostly focusing on the entanglement entropy. I'm thinking I have a 1D system. I take an interval of size A, and I'm going to call its length LA. And rho A is the reduced density matrix in A. Okay, so A bar is the rest of the system. And volume low will be this entanglement entropy is going to scale with LA, and otherwise it's going to be a constant. So, all right, so what example do we know of this? So I think the first example that was discovered is what you heard from Maxime yesterday, is the MBL transition. So I think, so I'll show you it's not the only one, for sure. So let me remind you a bit about what Maxime told you about, okay? So you have a spin chain and you have disorder. I'm going to call it W. Right. Say, just to make things concrete, I imagine I have, say, a spin 1/2 chain, and I put disorder, this field disorder. And this is in a box distribution of width W. And so what is widely believed is that you have a phase transition in this model, but not in a ground state, not in the free energy, but in the dynamics or in excited states, where at weak disorder, your system satisfies ETH. So it's thermal, it thermalizes. So what it means is that the reduced density matrix looks thermal. And here I'm going to think of eigenstates, say, in the middle of the spectrum. So your entanglement entropy will be fixed to be the microcanonical entropy. There's basically the maximum it could be. So it's going to be volume law with a coefficient log2. Okay, so that's what ETH would tell you. But if disorder is larger than some critical disorder strength, you get this MBL regime. And again, as Maxime talked about yesterday, there you get area law entanglement in 1D that your entanglement is going to be constant. It isn't going to scale with. So that's obviously an example of what I call entanglement transition. It's a transition from volume law to area law. So you can think of this as a transition, again, either as a dynamical transition of thermalization versus localization, or as an eigenstate transition, where you just diagonalize this Hamiltonian, but instead of thinking about the ground state, you're going to think of eigenstates basically in the middle of the spectrum. So here the mechanism is very clear. Well, okay. The sense that what the two things that are competing are thermalization versus localization, right? So, and again, you heard about the different phases during this workshop about ETH and thermalization, or about MBL and what we understand about MBL. But of course, if you see this phase diagram, the obvious question is what is going on here? Okay. And is there anything of these around these points? Is there some universalities the same in all spin chains where we have an MBL transition? Can we have critical exponents? Is there some renormalization group approach that will allow you to kind of understand what's going on? Okay. So I'll try to talk about, I will talk about this, but a bit later. But that's the first example of what you could call an entanglement, some entanglement transition. Okay. All right, so I don't want you to think this is the only example of such entanglement transition. Otherwise, the title of my talk, of the lectures, would have been MBL transition. Okay, so I'll give you right away another example. Yes. Yes. No, I don't think so. There's nothing. So I'll get back to this once I describe them. So here, the way we understand the MBL phase is like I will talk only about phase, like a phase where you have full MBL. That is to say, you have those local conserved quantities that Maxime was talking about yesterday, those Lioms or L bits. So you have local operators that commute with the full Hamiltonian. So all eigenstates will be localized here. So we'll only talk about cases where you don't have what's known as a mobility edge or anything like this, where you have full MBL, fully localized, the whole spectrum is localized, and here my whole spectrum is ETH. But I'll get to this. Where's the dynamic? So you will see this phase transition if you did dynamic. So it's like two ways of thinking about this phase transition, right? So you can either think of it again as an eigenstate transition, meaning you diagonalize this Hamiltonian, and again, you pick an eigenstate in the middle of the spectrum. But of course, that's not what you would do in experiments, right? You're not going to get an eigenstate in experiments. What you would do is a quench, right? You would start from an initial state, and you would time evolve, and you'll see dramatically different pictures here. Okay, so here you'll have no transport. You'll have things will be localized and won't move. You'll have this log growth of entanglement that Maxime talked about. Here you will have some transport. It's actually not diffusive near the transition, but you have sharply different properties in terms of dynamics of those two phases. But for now, I'm going to focus on entanglement. Okay. Any other question? Yes. As a function of disorder. Oh no. So yes, Yes, I know like there's another type of, okay, yes. But thanks for the question. So I know like this term dynamical phase transition is used for various things, including those singularities in the Loschmidt echo. So here, I mean dynamical phase transition in the sense that it's a transition and it occurs in dynamics. Okay. So it's not a singularity in time, it's more like those, if you do dynamics and quench experiments in those two phases, you're gonna find sharply different results. Okay. So it's more that it's a transition that will show up only in dynamics. And there's nothing in the free energy or in thermodynamics. Anything else? Okay. All right, so let me do another example. This is what I'm going to call measurement-induced transition. And so I wrote some references here. They were first introduced numerically in those two papers, if you want to have a look. And so in the rest of the lectures, I will mostly talk about the theory of those transitions, which would be those two papers here. All right, so here the idea, okay, so here the idea was thermalization versus localization. And here the idea will be to have two things that will compete. One will be chaotic dynamics or thermalization, which will lead to entanglement growth. And having local projective measurements, which will basically disentangle the system. So the mechanism will be chaotic dynamics. So this leads to entanglement growth. Versus local projective. So, all right, let me make this a bit more precise. Yeah, so I'm going to imagine I have, again, a 1D system where I have Q dits. I have n sites and a d-dimensional Hilbert space on site. So you could take, to model the chaotic dynamics, in principle, you could take any non-integrable quantum system you want. To make things tractable, we're going to model this by a random quantum circuit. So I'll explain what this is in a sec. I'm going to take a random unitary circuit. Okay, so try to draw this. I have my 1D system, and I will act on it with unitary gates, which are local and are completely random. So you have, so each box here is a random unitary, a random gate, if you want. Okay? So it acts only on two sites. So it will only couple nearest neighbors. So you have locality in this system. Okay, so there's no energy conservation, there's no Hamiltonian, nothing here. Okay, but so those are models that have been studied by many people, particularly Adam Nahum and collaborators. I'm not writing the references here. And you can compute many things. They show chaotic dynamics, and in particular, they have linear entanglement growth as a function of time, which will saturate to something like volume law entanglement if you have a finite system. Okay, so this is basically just to model the chaotic dynamics. This is not necessary to have this transition, but it will make the problem tractable. So this is, again, not really physical or necessary. You can do numerics with any non-integrable system you would want, and this will have this transition. It's purely for technical reasons that I'm doing this. So, okay, so the idea is like this random circuit is going to make entanglement grow generically, and it will lead to this volume law entanglement. So the way we're going to try to counteract this is by making measurements on the system. So what I mean by this is that on every link here, with a given probability P, we are going to measure, as in quantum mechanics projective measure, the spins. Okay? So each blue dot here is a projective measurement. And I'm going to sprinkle them with probability P. So let's say if you have a spin 1/2, right? So you really measure locally the spins and you get either up or down with a probability that depends, of course, on the wave function, like usually in quantum mechanics. Okay? But at the end of the day, you really project onto the outcome that you had, right? So I always remain with a pure state. I start with, say, a pure state and a product state. I time evolve with my unitary circuit. And every time you make a measurement, you make a choice. You flip a coin and you see what outcome you have. Say you measure that spin was up, you keep it to be up, and you keep going. So I'm not going to think about mixed density matrices or anything like this. I always have a pure state. So that's important. So it's thinking of quantum trajectories if you want. Okay, so you can easily see why this is going to lower entanglement. So let's say you had P equals 1, meaning you make measurements on all sides. That's basically meaning you measure all spins. And you will find that this spin says up, this one is down, this one is up, this one is up, this one is down. And at the end of the day, you just have a product state, which has 0 entanglement. So the other way to think about this is you're entangling whatever those spins with the measurement device. But I'm not going to think about that. Okay, so I'm just going to think of projective measurement as something that's non-unitary, that's going to disentangle my system effectively. Is that okay? Right? So if you again measure everything, every spin, you just get a product state. So this has 0 entanglement. So it's pretty clear there's a competition between the two. Every spin, but with probability P. Yeah, so with probability 1 minus P, I do nothing. So here I don't have my circle. But with probability P, I choose at random, and every time I had a blue dot here, I meant I made a measurement. Yes. I project. Right, so say I will take my wave function, say I have spin 1/2 again, I will say, I take my wave function overlap with spin up on this square, that's my probability of being up. With that probability, I'm going to project that spin onto being up. Okay? And then normalize again. And same thing for being down. So it's really like, what you learn with what a projective measurement is in quantum mechanics. Okay, so it's non-unitary, it's non-linear, but it will project back after the measurement, that spin will either be up or down. Yeah. So again, if I measure the whole system, I will just get a product state at the end of the day. What do you mean? It is a pure state after the measurement. So I'm thinking of quantum trajectory, so I will always have a pure state at all time. So by quantum trajectory, I mean you make a choice, right? You end up with up or down, and then you keep going with this. And then I'm gonna, okay. Okay, so this model, they were introduced in those 2 papers, and they studied numerically what this does. Okay? And what you find is this actually provides another example of something that is an entanglement transition. Okay, so how do you see this? So you start from, say, a product state with 0 entanglement. Yes. I do local things, right? So I project on this spin being up or this spin being down. But only that spin, it's local. I don't do it everywhere. I do it every site with probability P. Okay, so once you time evolve, I just do this with probability P on each site, and then I move on to the next layer. So only if P is 1, it's completely trivial. You just do it everywhere. Yeah. But if P is not 1, you're just doing it for a finite fraction of the spins. Okay, so you can look at your entanglement entropy as a function of time. Okay. So if P is 0, or if P is small enough, what this entanglement entropy is going to do is just grow linearly. Okay, so, and then it will saturate if you have a finite system, finite entanglement interval, it will saturate to something that's proportional to size of your interval. So that's volume low entanglement. And so this curve would correspond to if my P is small enough, But if your P is large enough, you do have a phase transition where this is just going to saturate and be straight regardless of the size of the interval, and you would get R yellow. So I'll actually spend a lot of time explaining why that's true and how you can understand this. Okay, so but there's a phase diagram, so now my tuning parameter is P, which is between 0 and 1. And you have a volume law phase here and an R yellow phase there. So if you measure too much, you basically project onto R yellow, meaning that SA at long times will go to a constant, but SA at long times will scale with volume here. So, and in terms of numerics, what do we know? So numerically, you see this phase transition, and you can try to do scaling and try to extract exponents from it. So people see like PC is around 0.2. It depends a bit on who you ask, but about this. Well, okay, if you have two states, so this qubit is just a qubit. Nu is around 1.3. So there's a critical exponent nu of a correlation length that looks to be around 1.3, and there's a dynamical exponent that seems very close to 1. So, yes. Okay, so my goal will be to explain what's going on here. Okay, so this is just a numerical observation for now. Okay, so that's what those two papers observed. As doing it numerically, you find as a phase transition, there seems to be a nice crossing, and there's an actual transition between those two. Okay, so if you measure enough, your system is going to end up in an R yellow phase where entanglement is not going to grow too much. But if you don't measure or measure a little, then you still have volume law scaling. Okay, so for now, let me just say it's an empirical fact. And again, like in the MBL transition, you can ask what is going on here. And you can ask maybe are those two related? Okay. The answer will be no, not at all. Okay. So I'll show that we can say many things. For example, I will show that Z equals 1 is actually an exact result here. So this transition actually has a dynamical exponent 1. All right. Let me quote a final example, and then I will actually talk about this a lot more. Okay. So the two examples I talked about so far are kind of very nice and physical or natural, I would say, right? So they're really in the dynamics. Either you tune disorder or you have this measurement device that will make local measurements to your system, and that's a way to drive the transition. So the last example I'm going to talk about is a bit more exotic in some way. And it's about random tensor networks. So it's a bit less natural. It doesn't have to do with dynamics, but it's very closely related to this one, and it's technically a lot easier. And so I refer you to those two papers if you want to know more. And in particular, the transition I'm going to talk about is in this paper. Yes? So you would not here. That's true. So there's no eigenstate here. Simply, I don't have a Hamiltonian, I don't have a flow K unitary, so there's really no notion of eigenstate. Everything is in the dynamics. So however, you can still talk about this. That's what I mean by volume law to ILO. But you're right, it's not an eigenstate phase transition here. But you still have this nice transition in the dynamics. MBL would be similar, except instead of ILO here, you would get log growth, right? Yes? Yeah. Yes. So the reason I introduced this random circuit is you'll see we can do many calculations exactly. So this is purely for a technical reason. So you can imagine actually what I'm doing is I have any chaotic quantum chain that you want that's giving you non-integrable chaotic dynamics. Okay, you can have a conserved quantity if you want or not. Like let's say energy is conserved. Then you make those measurements with a given rate in time locally. And people have done this with DMRG, and you see that phase transition too. So the reason I'm basically throwing away the quantum chain here and replacing it with this random circuit, because this will allow me to derive many things exactly. So it's a purely technical. Yes? No, so chaotic, I mean non-integrable, meaning ETH. So I don't know what quantum chaos means. For me, it means ETH. Yes. Yeah, so, okay. So here in the sense, of course, there's no, you're right, so there's no, what I mean by this is since I have no energy quantity, no conserved quantity, sorry, there's no energy conservation here. The system, if you want, you can think it thermalizes to infinite temperature, right? So there's no conserved quantity. That's what your random circuit does for you. So it's chaotic in this way. You forget your initial condition very quickly. You just get like a featureless state. Okay, okay, so chaotic, it's in the sense, I mean non-thermal, yeah, I mean pretty much thermal, will thermalize, and here it thermalizes to something trivial. Anything else? Okay, so let me do the last example, which will be actually closely related to this second one. Okay. So this one is about random tensor network, so it has no dynamics, but it's a way to represent just a wave function. So let's imagine you have lattice, so a square lattice, so it could be any graph you want. Okay. It's and this, you should actually think of this as a tensor network. So what I mean by this is on each node here, you have a tensor. Okay. And you'll have physical degrees of freedom. Maybe I should draw it a different color. And so your physical degrees of freedom are like external legs on your tensor network that will live at the boundary. Here it shows them to live at the upper boundary. Okay, so I'm using like standard notation for tensor network here. So each line means a tensor contraction. Okay? So typically, when you think of tensor network, the type you hear about are like if you do DMRG or TEBD, you think of matrix product states, which would be like just the top layer of this. Okay? So you have physical legs and you connect them by matrices. Okay? So that would be an MPS. So here, imagine I have more layers. So this is what something you could think of this as a PEPS or something like this if you're a tensor network expert. Okay, so it's like a 2D tensor network, but usually in PEPS or in 2D tensor network, people put physical degrees of freedom on each side. Here, I'm not going to do that. I'm going to imagine that I just have a wave function. It's 1D. It lives at this upper boundary. And I have like many layers. Right? Okay, so it's highly impractical for numerics. People definitely don't use this. Okay, but you can definitely think about it. And actually, the way I'm going to think about it in a way that's a bit similar to this random circuit, I should say here. So, okay, you had a time direction going this way. So here, I'm actually going to think of this as like some kind of time in the same way, except there's no unitarity. Okay, so I'm acting with layers of tensors. So again, each node has, indices, and I'm going to associate this like with a tensor mu, nu, eta, delta. And each line here again means a contraction. And then I have dangling legs, and those are my physical degrees of freedom. Is that okay? So if you're used to like matrix product states, again, I'm just adding layers behind it. So the game is you should contract this whole tensor, and this will give you a wave function. Okay? And so the physical degrees of freedom live here. So my physical Hilbert space is this. So I have, again, my Hilbert space is just a 1D, 1 plus 1D quantum system. But my tensor network is kind of 2D. And so you'll see why I do this. The reason I'm doing this is I want to encode more entanglement than a matrix product state could. Okay, so a matrix product state can only encode area-low entanglement, okay, at fixed bond dimension. And here, in order to avoid this, I'm just going to add many layers. And so this will actually be able to support volume low entanglement for the wave function I have here. So this is, you can think of it as similar again to the random circuit, except the only difference between a tensor and a unitary is unitarity. Okay, so this is like this quantum circuit, except you forget about unitarity. Okay. So why am I using tensors here? So, okay, I'm just trying to give different examples. So this one is a bit more abstract, but maybe more natural for people who do quantum info. So, it's well known that tensor networks are the right way to think about entanglement, right? So, like, and if you want to think about entanglement structure, you want to think about tensor networks usually. And the reason DMRG works so well is that because you have area law scaling of entanglement in ground states, and so you can gapped ground states, and so you can represent your wave functions as matrix product states. Okay, so here I want to think about, can I just take a wave function? There's no even Hamiltonian. I want to think, that's my wave function. It is defined by this tensor network. Okay? And I want to think about generic properties of entanglement of that wave function. Okay? And I want to ask whether I can have, again, a type of phase transition like in that model. And you'll see that it's possible. So the reason I'm adding like those layers is, again, I want to be able to get more entanglement than a matrix product state. Yes? What's happening here, or the nodes? Okay, so the tensors I'm going to take to be random as well. So just like in the random unitary circuit, and I will actually work more with this just to show you how you can understand those transitions. So I'll define precisely what I mean, but I'll take them to be random numbers. And so again, there's no unitarity. That's basically the difference. And so you can think of every layer here. You can think of it as like doing time evolution, like I said, but without unitarity. So in other words, you can think at each layer like this as a random matrix product operator. So like, again, tensor network inclined. So this is a random MPO, matrix product operator. It's like a matrix product states, but it has legs coming, it has bra and ket, so it's an operator. So the only variable here that I have is what's known as the Born dimension. I'm going to call it D. So this is just all my states run from 1 to D. That's just the number of degrees of freedom on each link. And so my claim here is that as a function of D, there's a phase transition in that model. And so I should say there's no Hamiltonian. Again, I don't have a Hamiltonian. I'm not diagonalizing anything. I'm just taking random tensors, doing this, and I get a wave function. And then I compute entanglements of, say, a finite interval. I call it A. And I try to compute this. And my claim is that as a function of D, so I'm going to take tau to be infinite. Okay, so I have infinitely many layers. And I'm also going to take an infinite system, yes, but I'll take a finite system LA that I scale to be up. Yeah. And so it's pretty clear you can have a lot of entanglement in this system, right? So, and I should say some people are doing this numerically, but of course it's not, no one is using wave functions like this as variational things, because those would be horrible to optimize, right? So, but in terms of theory, there's no problem with constructing a wave function like this. Okay? What's that? No, nothing is unit. No, MPOs are not unitary. No. Yeah, so that's the thing I'm gonna argue is that this transition is extremely closely related to this measurement-induced transition. And physically, you can imagine that each measurement is making something non-unitary, so you lose unitarity in any way. Right? And so effectively, and this one will end up being a bit simpler technically. But those are basically essentially the same type of phase transition. So, okay, let me just write down this. So as a function of D, there's again a phase transition in this model from area law for your wave function to volume law. And I should say you can here define D as the Born dimension, which is usually an integer. but there's a very easy way, and if you want to know more, I can talk about this offline, to make D a real parameter. Okay, so there's no problem making it real. Okay, so I need to tune it here. And my claim is that there's a critical point. If your bond dimension is too small, say the bond dimension is 1, you basically get a product state, so you have 0 entanglement. Okay? But if the bond dimension is large, actually it doesn't need to be that large in practice. When you do numerics, you quickly get volume law entanglement with something random like this. So again, this one is a bit more abstract. I mean, or whether you like this or not depends on whether you like tensor networks. But essentially, it's very similar to this. Okay, so that's what I'll talk about. All right, so those are my 3 examples. And so for the rest of these lectures, I want to basically unpack this a bit and give you in detail what we understand about phase transitions in those models and how they're related. There could be more. I should say I'm just giving 3 examples. It's very possible there are other examples of entanglement transitions. Those are the ones I know of. To be honest, I don't know more right now, but there could be more. And so what I will talk about mostly will be those 2, like random tensor networks and measurement-induced transitions. And again, all the references are over there. And I'll try to show you we can do a lot of things analytically for those models, and we can understand what those transitions are. And so in the end, I will also try to spend like half an hour or something on the MBL transition to tell you what we think we know about it. Okay. So all those indices in those tensors, they run from 1 to this bond dimension. Okay. So like in DMRG, that's the parameter that would control your calculation. That's the size of the tensors, basically. So those are, sorry, so those are just called like indices. So each leg is an index, right? And I contract them. Yeah. Oh, okay. So I'll explain what I mean precisely. So I will take them to be Gaussian distributed with 0 mean and just, some variance. And so I'll make this more precise actually because I'll work with this. But I'll take average of t to be 0, and I'll take something like t star t to be some number, and I will force all the indices to match. So I'd basically take them to be completely random coefficient and correlated. That's what I mean by random. So and the idea here is like, so I should say that this type of model was first introduced in the context of more high energy physics, okay, in that first paper by the Stanford group, okay, and they called these holographic tensor networks, okay, and they're actually meant to be like a model for ADS CFT, and I'm not gonna go into those details. I will kind of explain why that's true in some limit, okay. But this direction is meant to be, so it's holographic because your system is at the boundary. Okay? And you'll see there's some analogy, loose analogy with some things in high energy physics and ADS CFT. So at least when the bond dimension is large. But for me, I just see this as a model, and I would like you to think about this in a way similar to the random circuit for this for now. Yes. Yeah. Yeah. Yes. Right, and you could reabsorb like the measurements into these and make them non-unitary. So the only thing that's going to be different at the end is the measure over the averages. Okay, and I'm actually going to argue again those 2 are like essentially the same transitions. Okay, and just I'll explain why they are the same. Okay, or like there's some tiny differences between the 2, but like they are essentially of the same class. Whereas I think the MBL transition is a completely different beast. No, so they're completely different parameters, but I'm basically thinking I'm tuning transition from a different angle, basically. So the analog of the bond dimension here would be the size, size of the Hilbert space over there or something. So yeah, so there's no really analog between those 2 parameters, but I'm thinking they tune the same type of transition. So if you want, it will be the same universality class, but it's kind of crossed in another way. But I'll get there. Okay, so let me actually maybe just make this a bit more precise. Okay. I'm going to abbreviate random tensor network as RTN and measurement-induced transition. So for now, I was just giving you facts about what those are. Okay, so now I'll try to just actually unpack this a bit and tell you what we know and what we can derive for those transitions. Okay. And again, I'm going to focus on like the papers with the arrows, which are like theory papers for these. Okay. So before I actually get more technical, let me write down what I'm going to derive and say, okay, what do we know? And then I will derive it. Okay. So contrary to the MBL transition, for those models like the measurement transition and this random tensor network, we can do a lot of things. And in particular, we can map the calculation of entanglement exactly onto a 2D classical StatMech model. So what I'm going to argue, and I'll give you a flavor of this. So there's an exact mapping onto a classical 2D StatMech model. So this StatMech model will have, okay, there will be a subtlety, which is there will be a replica trick somewhere. So I'll have to deal with the replica limits, but otherwise it's still just a 2D StatMech model, and of course we know a lot about 2D StatMech models. So I'll use this here. So in some way I'm going to relate this weird entanglement transition to something a lot more traditional. Okay, so how does the mapping work? So this mapping gives you a very nice and simple qualitative picture. And in some cases, you'll see it can even give you exponents in universality classes and so on. And so the qualitative picture will be the following. So I'll have a StatMech model, so say something like an Ising model, but more complicated, right? And the entanglement entropy is going to correspond to the free energy cost of adding a domain wall at the boundary. So let's explain what that means. All right, so more precisely, so what does it mean? So I'll have a 2D as a function of parameters, so that could be P or D in that model. So my 2D StatMech model will live on that graph I defined, so like a square lattice here. Okay, so it will be defined on this square lattice. For the random unitary problem, it's defined on a more complicated lattice, but it's not that important. And I have my like boundary system A here. That's my system. And so in that StatMech model, what will happen is that you will have different fixed boundary conditions here. So let's say I have an Ising model. Essentially, with this entanglement calculation, will end up being the partition function of, say, an Ising model, where your spins are fixed to be, say, up at the boundary, but on that entanglement interval, they're fixed to be down. Okay, so I'll show you why that's true. So effectively, what this will do is, let's say your Ising model is ordered, and you have a ferromagnet. So all spins want to align. So what this is doing is like creating a domain wall. Again, like all spins are up in the bulk. But at the boundary, you're forcing spins to be down, so if you effectively create a domain wall. Okay. And so this phase transition as a function of D or P, and that StatMech model language will end up being a simple ordering symmetry breaking phase transition. That is, like your StatMech model in one phase will be a ferromagnet, in another phase it will be a paramagnet. Okay. And so here, same thing, you will force your, okay, I'm imagining I have Ising spins, which is not quite the case, but okay, so same thing, you force a domain wall. So here you can very clearly see what's going on. Okay, so let's admit this is true, that the entanglement entropy is just a free energy cost of creating a domain wall. So if you have a ferromagnet and you create a domain wall, okay, and you ask about how much it costs in free energy to create that domain wall, it will scale with the size of the domain wall. Okay, so in particular, let's say you're at 0 temperature, you only have energy, it's clear you just pay an energy cost at each link, right? So if you have a big domain, it costs an energy that scales with the domain. Meaning your free energy is going to scale with the size of the domain wall in a ferromagnet. So that's true in an Ising model. So now let's say you have a paramagnet. So now your spins are completely disordered. Or in other words, if you want, you have a domain wall condensate in the bulk. Okay. So now if you create a domain wall at the boundary, you can just go like a couple of correlation lengths into the bulk and absorb that energy cost. Okay. So in other words, like the free energy cost for creating a domain wall here scales as a constant. Okay. So this is a simple fact about just 2D classical statistical physics. You ask about how much it costs to twist a boundary if you want to like create a domain wall. It will scale with the size of that interval if you have a ferromagnet or not if you have a paramagnet. Okay. And so what I will show, what I hope to show here, so paramagnets is like a domain wall condensate, right? Is that this is the simple mapping, and it gives you a very, again, intuitive and nice picture of what entanglement is doing. And obviously, again, we know a lot about 2D StatMech, right? So it's much easier to compute partition functions and free energies than entanglement. But that's kind of the classical, the picture we have here. Okay, so that's what I will derive. With the caveat that the StatMech model will be a lot more complicated than Ising. Okay. But the physical picture is the same. And so now that phase transition, right? Well, it's only this transition here between ferromagnet and paramagnet. Okay, so that's one other nice thing. Here, in that language, the entanglement transition is just an ordering transition for the StatMech model. So when your StatMech model is ordered, you have volume law phase. When your StatMech model is disordered, you have a area law phase. Okay. And in particular, the critical points will just be the critical point of that 2D StatMech model, and it will be described by a conformal field theory in 2D. The critical point will just be a 2D CFT, and so I will hopefully get there, but just so the caveat is it has control charge 0 for those of you who are like CFT experts, so it's a non-unitary, unpleasant CFT. But it is, you know, I can write down at least a Lagrangian for you, and some things like I promised to have field theory calculations for this. Okay, so this, I'll get to this. This comes from the fact that I have a replica model. So it's not an Ising model, something. So what I mean by this is like the entanglement transition in this dynamics, in this measurement, or in this random tensor network maps exactly in that language to this calculation in the StatMech model. So I'll show this, that you can show exactly that the entanglement entropy is a free energy cost in this StatMech model. And so now this entanglement transition for the entanglement entropy is going to end up being just an ordering transition for that StatMech model. Okay? So this is not really an equal to, it means it corresponds to an ordering transition in this language of statistical model, okay? Which is a lot easier, I should say, obviously, than an ordering transition in a classical StatMech model. It's a lot easier than the problems I started with. Right? I started with complicated dynamics, quantum dynamics, and computing entanglement. I end up with a partition function of a 2D StatMech model. Yeah, so here think of it as D for the bond dimension, or it could be P and PC for the measurement problem. It's true for both things. Okay? Yes, 1 minus P. Thank you. Yes, yes, that is correct. Okay, good. Yes. No, not that I know. Well, okay. I should say I don't know. Okay. Let me postpone that question until I actually tell you about what the transition, what we think the transition is. But yeah, okay. So one thing I should say is if this is true, I mean, it kind of naturally gives you conformal invariance at the transition, which immediately implies that you have dynamical exponent 1, of course. Okay. which is something people saw numerically. So it's kind of remarkable if you think about this measurement transition I was describing, right? So it's something where space and time have no reason to scale in the same way, right? I mean, you have space and then you make those unitaries and you make those measurements. And it ends up being, at the end of the day, if you, like, from this exact mapping, you get a transition where at the transition you have this emergent conformal invariance, and in particular space and time scale in the same way. So it's a relativistic field theory as a, okay, so it's a lot more than this, it's conformal, okay? But in particular, it has z equals 1, which is highly non-trivial. And I will argue like the MBL transition is dramatically different. For the MBL transition, we actually think z is infinity. So it will be like completely different, okay? But this one is a nice transition where L, well, basically length scales with time with a simple velocity in between, at the transition only. Okay, so it's an emergent conformal invariance, it's only at the transition. And so another thing you can derive is that, so I told you, like at the, told you here you have a volume law phase and here you have an area law phase. Okay, you could ask, what about what do I have at the critical point? And from this, actually, mapping that I wrote and just knowledge of standard quantum, just critical phenomena, you can easily convince yourself that the entanglement entropy or the free energy of creating a domain wall scales as log L at the transition. So I won't talk about this too much. But this is also something that's known and seen as numeric. So as a function of time, it scales as log T, right? So it scales as log T, and then it saturates something that's log L. So the reason being like this difference of free energy for creating a domain wall at a critical point ends up being the log of a two-point function in conformal field theories. So if those of you are like CFT experts, this corresponds to boundary condition changing operators. Okay, so this corresponds to changing the boundary condition. So again, I won't talk too much about that, but this is just in case you like CFTs. This is the log of a two-point function, and so you know how it scales. So this is not the entanglement entropy of the CFT, right? So, okay, so you're probably thinking of like the Cardy-Calabrese formula, right? So this doesn't obey the Cardy-Calabrese formula. So this is an indirect mapping, right? So there's the entanglement of my quantum system that I'm mapping onto this classical system. That classical system is 2D, and at the critical point is described by a 2D CFT. Okay? So this entanglement is not the entanglement of this 2D CFT thought as a 1 plus 1D CFT. It's the entanglement in my original model, which is this measurement transition or the random tensor networks. Okay, so this has a coefficient which is not the central charge of the CFT. Okay? It's actually has to do with the scaling dimension of this boundary condition changing operator. Okay, so this is only, again, I don't want to dwell on this. This is just in case it makes sense to some of you, okay, but it's, if you know about CFTs and boundary condition changing operator, probably makes sense. Otherwise, you can just trust me that just from simple CFT scaling, you can see this is correct. Okay, so the question you're asking here about the CFT is not entanglement of the CFT. It's take your CFT and do this. Change the boundary condition and compute the ratio of partition function. And it turns out it corresponds to inserting operators here at the boundary, which are known as boundary condition changing operators. Yeah. Yeah, so I mean, the type of critical point you should think about, again, I'll get back to this. I mean, I will get to C equals 0. Okay, so the type of critical point that you may know that has central charge 0 is like percolation. 2D classical percolation is a type of CFT that has central charge 0. Okay, so the type of phase transition that has trivial partition function. Okay, and so finally, let me just mention how do I see conformal invariance, and mention we have Z equals 1, but we have actually a lot more than this. People have even probed conformal invariance. So how do we see this? So you take your system, your 1D system, and you take it with periodic boundary condition. So you take your like whatever system, and and I'm going to put it on the ring, so like my physical 1D system now. And instead of considering one interval, I'm going to consider two, A and B. And now I have like, I'm going to call this x1, x2, x3, x4. And from this exact mapping, you can also compute what's known as the mutual information of A and B. And from this free energy, whatever trick, the same here, you can show that, again, that at the critical point, it corresponds to a 4-point function in your critical point or in your CFT if you want. So what it means is that it's going to depend, in principle, it could depend on all my x1, x2, x3, x4. And in practice, it's only going to depend on a particular ratio, which is defined in the following. So this ratio I call eta, and here xij is like the chord distance, so it's something I have a periodic boundary condition, so it's sine xi minus xj phi divided by L. So it's a distance when you have periodic boundary conditions. Okay. So this is just a consequence of conformal invariance. So this essentially ends up being a 4-point function, and something you know from conformal invariance is 4-point functions scale like this. So this is a really, again, weird fact. You just compute this mutual information. You have two intervals and all those coordinates at criticality. And what you find is that people did numerically, in particular, there's a second paper by Matthew Fisher and collaborators that did this. Okay? So you do this numerically, you try to plot your mutual information that depends on all those variables, and you see that it collapses onto a single curve that depends only on this parameter eta, periodic boundary conditions. Okay. So it's a very strong probe of conformal invariance at the transition. Okay, so that's the fact that it collapses onto a single curve. So it basically tells you this mutual information is conformally invariant at the transition. So, okay. All right, so this is also seen numerically. Okay, so is there any other question? Because my next step will be to show you why I can do this mapping. Okay, so that's the whole picture, basically. Okay, so now I'll get to the technical stuff, where it matters less if I don't get to the end. Okay, and I'll just try to derive and give you a picture why this is true. Okay, and once this is true, everything else kind of follows, and you get all those scaling properties. Yes? Yeah. Yes. Okay. Yeah, so what I'm going to do is derive the StatMech model for you in the case of random tensor networks, okay? We can discuss offline. I can tell you how you do it as well for the measurement transition with the random unitaries. It's just more technical and harder, but it's the same logic. You can do pretty much the same thing, and you can map it onto. So everything that I told you applies both for the measurement transition and for the random tensor networks. All right, so I kind of started with the results and postponing the actual calculation to the end. So now I will actually get to explaining why this is, or everything that I told you is true. So why is it that I can map things onto a StatMech model? And I should say it's highly, non-trivial that you can do this, and in particular, it gives you all those features, which are absolutely non-trivial if you think of those problems in the first place. Why should you have conformal invariance here? Yeah. I mean, everything I wrote is like 100% true just from conformal invariance only. I haven't said anything non-trivial for anyone who does conformal field theory here. Like this is, I've not used any non-trivial exponent. All of this is true just by conformal invariance alone. Yeah, I mean, it's a 2D classical StatMech model. So, I mean, I could have a first order phase transition. However, I mean, we'll see how it's derived. Like in the replica limits, it's highly unlikely. I mean, I'll get to that. Like it usually doesn't happen in the way it's done. But like if it's second order, you should just have a CFT in 2D. It's a stat-mech model. I mean, it's anisotropic, but okay, yeah. Yeah, I mean, like in 2D stat, yeah, okay. I mean, it's not that, I mean, actually in the random tensor network, it's actually isotropic, so it's not even, yeah. But everything I wrote is kind of like true in general. All right, so I'm going to focus on random tensor network. So I know it's the most exotic example in terms of what I talked about, but it's also the simplest one from technical reasons. So, and if you want to know about the measurement transition, you can look at those two papers. It's just like a bit more involved to actually do this mapping. So again, my problem is still there. So I have a graph, I call it G, which is a square lattice. My physical system is living at the boundary, which is here. Okay. And I want to compute entanglement entropy. And so in particular here, I'm going to focus on Rényi entropies, not only von Neumann, okay, which is just trace of rho a to the n. So two things here. So I'm going to want to compute this quantity averaged over all possible choices of my random tensors. So that's what the bar means. And if I were doing measurements, I would want to average this over all possible random unitaries, but also measurement outcome and places where you put the measurements. Okay, so it's kind of one big average. So the other thing you should notice is I put a trace of rho to the n factor here. This is just by to normalize things. So in particular, there's nothing that tells you that the wave function I wrote there is normalized in the way I do it. So I'm just going to like get a wave function and then normalize it afterwards. So it's the same, okay, when you make measurement, you also have normalization issue, right? Every time you project, you lose some norm, you have to normalize. So this trace of rho to the n is just to normalize things properly. Okay, so that's what I want to compute. So it looks bad, right? So I want to average a log of a ratio of all those things over all of this, okay? So it looks highly untractable until you realize, okay, you want to average a log. So usually when we want to do this in physics, we try to do a replica trick. Okay? So I'm going to write an exact formula, which is just replacing the log by the following limit. Trace of rho to the m minus trace of rho n. All right, so let's stare at this formula for a minute. So think of m as a real parameter. What I wrote is just true. You take this, take a derivative with respect to m. Okay, so that will bring the trace of rho to the n down, and then m to 0. Okay, so if you take this formula, compute this derivative, and take the limit m to 0, you do get this. Okay. So the trick, though, is that this is a replica approach. So what I'm going to do is actually compute those things for m integer. And then I'm going to imagine I take m to 0, okay, as a real number. So that's the usual thing you do when you have a replica trick. Okay, and so what I'm going to claim is that those quantities are actually a lot easier to compute when you do the average and you don't have the logs. Okay. So this is nothing but a replica trick. Okay. A bit just in the context of this. Okay. Right. So I'm going to let ZA be this quantity, trace of rho a to the n, everything to the m average, and Z naught to be the same thing but with trace of rho. And so I'm using a notation that is suggestive. You'll see those are actually those are the partition functions I want to talk about. Okay. And so we have that ZA to the N average from the formula I wrote over there is, so you can recast it in terms of free energies. So limit of M goes to 0 of 1 minus N, this derivative of a free energy difference FA minus F naught, where I have defined my free energies as minus log Z. So this follows from the formula I wrote over there. And I've used the fact that those two partition functions are actually trivial when I take the replica limits, right? So if I take M to 0, they just become 1, right? So my partition functions are actually trivial, exactly in the limit I care about. However, you see I don't care about the partition function, I care about the derivative with respect to M. This is gonna make everything non-trivial. So that's the actual key formula I'm gonna use. So you can already see this free energy difference I was talking about. Okay. So now all I need to do is that indeed those things are indeed partition functions of something. Right. So now I don't have to average a log, but I do have to average traces of like powers of a density matrix. Sorry, rho is my density matrix. So rho is just, I take my wave function and I form just a pure state. So rho is just my wave function, density matrix of my wave function. Of my full tensor net. So I take my tensor network, it gives me a wave function. Rho is just this. So this is not normalized. It's not normalized. So this indeed is also the same as trace of rho to the NM. So that's true. I mean, it's just a constant. I mean, the point is like the norm of the wave function is non-trivial. Okay? It's just a number. I don't know. So yeah, trace of rho is not 1. Like just the way it's constructed, I don't know what it is. And it's going to be something non-trivial. Okay, so indeed, that's actually the next thing I was going to say, is you can think that Z naught is just trace of rho to the tensor NM. Or like, if you want, it's like trace of rho to the NM. Okay, so I have various ways to write this. I'm actually going to write this trace of rho to the Q, where Q is N times M. Okay, so it's just I take Q replicas of my density matrix and I average. Oh. Right, so you're asking how I reintroduce the logs here? Yeah, so the reason you can write down logs is, okay, you don't have to. So actually you can either write ZA minus Z0 or FA minus F0. So both are correct because ZA equals Z naught equals 1, that limit. So taking a derivative of the log, right, it's like Z prime divided by Z, but since Z is 1, it's like taking Z prime, yeah. So this just makes it more suggestive. It's a free energy cost. So that's why I have logs back here. But what I have to compute though is just those Z's. Okay, so I'm gonna ignore boundary for now. So that is, I'm not gonna think of my entanglement interval. And so I want to give you a flavor of why I'm actually going to derive why this does map onto a StatMech model. So what is it that we're trying to do here? Again, we have this tensor network. Okay, so we have Q copies of it, and then we want to average. Okay, so we have like nodes in your tensor network, right? So I'm just going to call this, say, T1, and say it has indices, and it has an index mu here, and say it's connected to another tensor I call T2. Okay, so mu is mu are the indices I'm contracting with this leg here. And so again, you have rho, and so rho has a ket and a bra, meaning it will have, each row will have some T's and some T star. okay, for each tensor. And now I want to average. And again, the rule for the average is the average of t is 0 of any like tensor. And the average, so the only way I get something non-zero is I do Gaussian averages. What this means is that if I have tensors on different sites, so I call this like I and j, so my tensors are uncorrelated if they have different sites. So I get non-trivial, it have to be the same site, and this also forces all indices to be the same. Only the identical tensor elements, if you want, are the same. So that's a Gaussian average. And of course, you have a Vic theorem for higher moments. So now you try to think about what we do here. Okay, so the only way I get something non-zero when I average is when I contract a t with a t star. But now I have several replicas. Let me try to draw a picture of what's going on. So we can actually compute that trace exactly, or we can rewrite it as a partition function. And so let's do an example, right? So say I have a site, I call it T1, and now I have T1 star, okay? So this comes from, again, Brian Kett. And let me consider a case where I have 4 replicas, and I'm just going to draw them. Okay. So T1, T1 star, T1, T1 star, T1, T1 star. Okay. So I'm considering a case where I have Q equals 4 replicas. So I have T1 that appears 4 times and T1 star that appears 4 times. And I have the same for the T2s over here. T2 star. Sorry, there. So we'll just need one example, and you'll see the general pattern is pretty clear. T2 star. All right, so that's supposed to be a picture of my wave function. I just focused on a given link. Okay? And now I have like all those tensors. Every time I have a star, it comes from the Brian, not the Kett. And I have 4 of them because I had 4 replicas. Yeah. Got a question? Oh, no. So now the rule of the game is I want to pair all those. So I need to pair a T with a T star every time on the single site. So for example, I could take, so I'm going to draw it this way. Okay, so I could pair this T1 with T1 star from the same replica, just doing this average. Okay. But now you can also pair things from different replicas, right? From this game here, so those are the same tensors. So that's what I'm going to draw here. So for example, I'm going to pair this T1 with a T1 star from a different replica. So this is my first replica, second replica, third replica, fourth replica. And you could say, pair this T1 star with the T1 and this T1 with the T1 star. So that's a valid pairing, for example. So if you want, it's like a Vic theorem for those. And you could do various things. So for example, we could have this one with this. Let's see what example that. Every time the rule is you should pair a T with the T star, okay, on the same site. Okay, and this one with this one, and say this one with that one. So that's on the separate sites. I just chose different pairings, and I should sum over all those pairings. Again, it's like a Vic theorem type thing that I'm doing. Okay. So what you see is you should basically, if you have one replica, it's trivial. You should just pair T with T star in order to get something non-zero. But if you have more than one replica, you basically have, you see you have permutations, right? So you could write, you could this T1, you could map to this T1 star, this T1 star, this T1 star, this T1 star. So on each site, basically this, so once you match the T and the T stars, on each site you have a permutation that tells you the pattern of the pairing. Okay. So the rule of the game is the following: you match Ti with Ti star, and again, if you want to think about this, this is like a Vic theorem in different replicas. And what you can convince yourself from this is that this will be a sum where on each side you're picking a permutation. And that permutation lives in SQ, the permutation group of all my replicas. And then you have a weight function of all those permutations you picked. So you can see the first step of my StatMech model here. My degrees of freedom will be permutations, actually. So this weight cannot be anything. So in particular, so here, I mean, the way I ordered my replicas is kind of arbitrary, right? I said this one is first, this one is fourth. So in particular, if you kind of reorder them, I should get the same answer. So what it means is that my weights should be invariant under multiplication by the left or by the right by a permutation. So, okay, those are just basic properties. You can convince yourself correct. So you have left, right multiplication by any element of SQ should leave the weight invariant. Okay, so it's a symmetry of the model if you want. So it's like reordering all the factors in row to the Q. So it means that you have an SQ cross SQ symmetry. So meaning it should be invariant again by left and right multiplication. And you can also see that it factorizes onto weights that live on links. Okay, so that's the part I'm not going to talk too much about. But so at the end of the day, you can convince yourself that it actually, you have a sum of the permutations. And now you have a product of the links, and the weight ends up being a function only of this combination, GI inverse J, where those are permutations. And C, it's what's known as a class function. So it's something that satisfies this property that it should be invariant if you conjugate by a given permutation. Okay, so I know this is more technical. I'll get back to less technical things after the break. Okay, so that's deriving this StatMech model. So what have I done here? I have hopefully convinced you that, okay, you can, the way you're going to do your average because of this Vic theorem, you need to get permutations. And now you need to compute this weight for the permutation, and it has this invariance, and you can rewrite it in this way. So now, in the last few minutes before the break, let me just try to tell you what the weight is, and then we'll have our StatMech model. Okay? And I'll have to tell you what happens at the boundary. So, okay, what is the weight? So we have all those pairings. So those pairings tell you that indices have to be the same in the tensors. So now you should also remind yourself that T1 is connected to T2. I said they were connected by a link, which also means you have contraction, which means also indices have to be the same. Sorry, did I miss? Yeah. Not straight, unfortunately. So all those lines mean that indices have to be the same. Okay. And so now at the end of the day, everything that's not, okay, so now you're kind of just summing over all the indices, right? So you have this contraction means indices are the same and you sum over them. So now the rule of the game is every time you see a line, okay, indices have to be the same, but within a given loop, you can have any index you want. And so this weight here, so on each loop, so the weight for this turns out to be D, the bond dimension, to the number of loops. Okay? And so the reason is in each loop you can have D degrees of freedom propagating. Okay? So D could be, you could have any of those D, but if within each loop those indices are forced to be the same. Okay? So in my example, I have 1, 2, 3 loop. So this is D to the 3. And so this beast in terms of permutation is known as the number of cycles, okay, the number of loops. So it turns out to be D to the number of cycles between permutation that shows on site I and permutation that shows on site J. Okay. So permutation GI was this one, permutation GJ was this one. So in representation theory and permutation group, this is known as the number of cycles in the permutation. All right, so I think I'm out of time for this first part of the lecture. So what I'm going to do after the break is just briefly tell you about the boundary of this. So we basically have our StatMech model now. I need to tell you what it does at the boundary. But basically from this, we'll have everything I told you before, and I'll tell you about how in some cases we can use this to even get exact critical exponents. In some limits, this StatMech model is going to simplify. Okay, so for now, it looks a bit ugly, but it will get a bit simpler. Okay. Thanks. Me.
I missed this, but at which point did you put n and m together? Because you had trace rho to the power n,
right?
Everything to the power m, and namely if you just plug in, it doesn't work, right?
Yeah, so no, it does if rho is a pure state. Right, so let's say I'm not doing trace of rho quite yet. I'm doing just rho. If it's a pure state, it's true. I could put my n and m indices all together. So there's a symmetry. You see that n and m here are completely together. Right, I have a SQ symmetry, and Q is n times m. So there's no distinction actually in the bulk of my tensor network between n and m. But you'll see at the boundary there is something special, of course. So that's what I need to tell you about here. G inverse, so G's are permutations, so like group elements. Okay, so that's the inverse permutation of. So I think of SQ as a group, right? And so this is inverse of that permutation times GJ. So you can convince yourself like this form has to be true just by this invariance. And this invariance is very natural. It just tells you that, again, you can reorder all those factors in some way and it shouldn't change anything. So here, for example, I drew permutations, right, in terms of those loops. And you can convince yourself, actually, it only depends on like this, well, this number of loops. And again, in representation theory, you can convince yourself it's this number of cycle and this permutation. Okay? So this is just words, right? But what matters is just that this is this number of loop thing I'm counting.
Any other? Oh, sorry.
Yeah, Roman, so I missed the last point. Is it now possible to task this model as a loop soup?
Simpler. So I have spin. I mean, it's not loops yet. Sorry. So my degrees of freedom are spins. And so my spins are those permutations. So the degrees of freedom are permutations, which is a bit unusual. But of course, if it's S2, it's just an Ising model. But if it's S10, it's a more complicated thing, right? So you have Q factorial degrees of freedom on each side, and the weight happens to be this d to the number of cycle on each link. Okay, so it's just a well-defined StatMech model. The weights are positive. There's no problem. So it's not a loop soup, right? So the loops just come from counting the weights. That's just like doing this Gaussian average, this Vic theorem, and doing this trace.
So the concept of cycle is only defined on each bond separately.
Yes, that's correct. Yeah, so I'll rewrite the partition function after the break, but it's really product over each bond. And on each bond, you have d to the number of cycles. So that's the precise StatMech model. Okay, again, it's more complicated than Ising, but it's well-defined, positive weights, and so on. And it could be ferromagnetic or paramagnetic.
So physically, this transition, it's kind of like a Zeno effect. So you keep measurements so frequently that it doesn't evolve. Is that right?
I mean, you can think about it as like, okay, it's not like a localization transition, but I mean, yes. I mean, you're measuring so much that you just disentangle, right? For me, I just think of Venta. Well, you're not localizing anything here. It's I don't know if I would call it Zeno.
Something I start see how this evolves. So is it true that in the localized phase it would kind of stay stuck?
No, I don't think so, actually. So I think you disagree, Sarang, or no? Oh, okay. So I don't think so. I think you only see this transition in entanglement actually here. So there's no transport property of this. It only shows up in the entanglement features. Yeah. So it's not. That's why I would resist calling it Zeno for this. But yes, it's making measurement and disentangling, but it's not localizing things. Well, that's also true. Yes. So I am actually thinking about this, but I don't think it stops transport to that phase. Yeah. No. Yes.
Good. So let's reconvene in half an hour. Okay. Thanks a lot, Roman.